Okay. So we talked about, so at physiological pH, which is almost neutral, it's a little bit under neutral, this carboxylic acid group is always deprotonated, and so that's why these amino acids come in their negative charge, the acids do. And then the amine group, which is a base, is always protonated at a physiological pH, which is why all the bases have the positive charge on them. And so the bases are lysine, arginine, and histidine. There's only 3, so it's easy to memorize. Same thing, the acids, there's only 2. There's aspartic acid and glutamic acid. Histidine, one thing is that the pKa of this one is, and then remember pKa is the negative log of the Ka, so negative log of the ionic form over the the weak acid form. And so at this pKa is very close to physiological pH, so it can either be protonated or deprotonated. So that's why this one doesn't have a charge on it, but it can just as easily have that H2 and then have the positive charge there. All right, let's go to polar uncharged. So we have serine, threonine, tyrosine. Serine and threonine, as you can see, there is no benzene ring, so these are aliphatic, and this one's going to be aromatic because of the aromatic group. They do all have the OH group, and you got to be really careful not to circle this one, because this is the carboxylic acid group, and the carboxyl group, every amino acid has that. So what happens is that kinases, which are regulatory enzymes, so that's a protein that goes around turning other proteins on and off because it's a regulatory one. How it regulates is that it has ATP, right, adenosine triphosphate, and it takes one of those phosphate groups and it adds it to the hydroxide group, or alcohol, hydroxide, whatever, of these amino acids. And because the phosphate group is negatively charged, it's very hydrophilic, and so it changes the structure of the protein, and that can either turn the protein on or off. Okay. Here are some more polar uncharged amino acids. This one's asparagine, and this one's glutamine. That's spelled wrong. Glutamine, okay. And then it says amide derivatives of aspartic acid and glutamic acid. And the reason why it says that is because how over here you saw the carboxylic acid group here with the C double bond O and then a single bond to OH. C double bond O, single bond OH. Over here they have the C double bond O, and the only difference is now it's NH2. Same thing, C double bond O, NH2, but has the same number of carbons here. So asparagine, aspartic acid, glutamine, glutamic acid, and the only difference is the amine group here, hence the kind of ending. So maybe those will be easy to memorize. Cysteine is, remember, these ones are really important because they create the disulfide bridges. So let's just say that this cysteine created a disulfide bridge with another cysteine. Are these amino acids being oxidized or reduced? So because they are losing the hydrogen, it's going to be oxidized. Remember, oxidized is either gaining oxygen or losing hydrogen. Reduced is either gaining hydrogen or losing oxygen. And so if they're in an oxidizing environment, they will form these disulfide bridges. Inside of the cell, they have like antioxidants, right? So it's inside of a cell, it's the reducing environment. And so inside of a cell, you won't have disulfide bridges. They'll just be in this form with the sulfur connected to the hydrogen. Okay, so let's go over this chart, and then this kind of stuff we have to memorize. So hydrophilic, the ones that like water, we have polar plus the charged ones, right? So the acidic ones are glutamic acid, aspartic acid, and you're going to see these in their conjugate base forms. If you see a negative charge on the amino acid, it's probably an acidic one. And then for the basic ones, lysine, arginine, histidine, they're going to have a positive charge on them, right, at physiological pH. So those are the basic amino acids. The polar ones, serine, threonine, and tyrosine, right? Those are the ones with the hydroxide groups on them. And then we have asparagine, glutamine, which kind of look really similar to the glutamic acid and the aspartic acid. And then we've got cysteine. So how many is that? 1, 2, 3, 4, 5, 6. Okay, not too bad. The nonpolar ones, glycine, alanine, valine, leucine, isoleucine. Those ones are really easy for me to memorize for some reason. Proline, remember that's the one that comes in a ring. Methionine, thio, that's the one that has the sulfur in there, but remember it was connected to carbons on either side, so it's considered nonpolar. Phenylalanine, it just has the benzene ring. Tryptophan, the biggest one. Okay, amino acid reactivity. Okay, yay, this is fun. All right, let me see. Okay, so amino acids are what's called amphoteric because they can be both an acid or a base. And so what happens is that you know how there are different functional groups that have a pKa. So for example, the carboxyl group, the carboxylic acid, it has a pKa of 2 because it is acidic. And then the amine group over here, it's a base, so its pKa is higher than neutral, right? So this is basic. It's about 9 to 10. What happens is that let's just say that that the pKa, right? The pKa is lower than the current pH. So for example, if the pH was 7 but your pKa was 2, then when you put that amino acid in there, it's going to pKa is you can kind of think of it as the pH at which the amino acid would be in equilibrium. So if your pKa is 2 but the pH is 7, that acidic amino acid is going to give up its hydrogen, right? It's going to deprotonate because it's the pH is too high over there, and they're going to lose that proton. But for example, if the pH was smaller, like for example, let's just say it was super acidic, like you're in the stomach or something, and the pKa is like 1. Oh no, the pH is 1 and the pKa is like 2. What happens is when the pH is lower than your pKa, there's so many hydrogens already in the atmosphere, it's so highly concentrated in hydrogens that the hydrogen can't pop off of that amino acid even if it wanted to. It'll be in its protonated form. So what happens is that when the pKa is less than the pH, it will be in its deprotonated form. When the pKa is higher than the pH, it'll be in its protonated form. So let's see. So what happens at physiological pH for an amino acid? Well, why don't we check it out? Let's just say that the pH is around 6.8. Okay, well that's higher than the pKa of 2 for a carboxyl. So if this is higher, then that carboxyl group is definitely going to lose that hydrogen, right? It's going to look something like, it's going to lose that, and it's going to be negatively charged over there. And then the ammonium, it's got that pKa of 9 to 10, but the pH is lower than that, right? There's too many hydrogens already in there for the ammonium to lose its hydrogen group. So it should just look like that. Let me see, is that right? Yeah. Okay, so I've just learned that, so when the pH is lower than the pKa of ammonium, then the ammonium is going to be in its protonated form, and this is actually its deprotonated form. Normally it looks like this, and there is that positive charge on there. So at your physiological pH like this is going to be what your amino acid looks like. It's going to have that the carboxylic acid part is going to be too acidic, and so it's going to lose that hydrogen. But this one, the pKa is a lot higher than the pH, and so the hydrogen is going to stay stuck on there, and so it's going to have the positive charge. When the amino acid is neutral, overall no net charge because the positives and the negatives cancel, we call that a dipolar ion. Because it has two charges, right? A positive and a negative. We can also call it a zwitterion. Zwitterion? Dipolar ion or zwitterion. Yeah. So that's what it's called. Okay. Oh yeah. Here are the rules. So when pH is lower than your pKa, then there's already too much hydrogens up there. It's going to be in its protonated form. When your pH is higher than that, it's going to be like yippee. It's going to go into its deprotonated form, right? In order to lower the pH there. Okay, and then you can see here that, so your ammonium group, it's going to go back and forth between being protonated and being deprotonated and neutral, and protonated and then positive. This one's going to go between being protonated at neutral and then deprotonated, which gives it the negative charge, right? And so this is the zwitterion. You can see that. And then you can also see that if the pH is low? No, if you have a very low, if you have a very, very low pH, then lower even than 2, then it's going to be too acidic for the hydrogens to pop off, and so you're going to have the hydrogen here, the protonated form here, and also this protonated form here, and it's going to be overall positive. When the pH is really high, it's in a really basic environment, it's already been deprotonated at both ends. So over here, when it gets deprotonated, it becomes a negative charge, and over here, when it deprotonates, it just loses the positive charge and becomes neutral. So at a really high pH in a very basic environment, it's going to be fully deprotonated. It's going to have that overall negative charge. Okay.